Hey guys, what's going on? So what you're watching here is a clipped video from a whole video that you'll be able to access if you become a member on Patreon or if you become a member on my YouTube channel. These videos are relatively difficult to make because I'm using multiple sources to compile all the information together. And so with your contribution, I'll be able to make more content as well as create exclusive content for those of you who are really invested into this channel, who really want to understand a lot of advanced physics and life sciences. So with that being said, make sure to hit the like and subscribe button. Make sure to go onto the Patreon page and you can contribute there. You can also become a member here on YouTube. So let's now get into the topic. Hey guys, what's going on? So today we're going to be covering conformal field theory. We're starting a new playlist here as well. Conformal field theory is something you probably have tried to go onto YouTube to learn about, but most of the stuff I found on YouTube is really abstract, really obscure, and sort of hard to understand. So over the past few, I'd say probably a year and a half or so, I've sort of tried to really understand conformal field theory, getting through a lot of the abstractions and a lot of the weird equations and everything to try to get a more intuitive understanding of this theory. Partly because this is just an interesting theory to me, and it plays a huge role in things like string theory and phase transitions and all this stuff. So without further ado, make sure to hit the like and subscribe button if you like this sort of content. Make sure to become a Patreon member or become a member here on YouTube. Either one, you should theoretically get the same benefits. So with that being said, let's go ahead and get started. So we're talking about conformal field theory. In conformal field theory, one of the things that we want to understand is the metric and how the metric transforms in accordance to how our reference frame transforms. And the key idea here is that the physics of things shouldn't change. So the idea, again, being that no matter what your coordinate frame of reference is, the physics, the underlying physics, the differential equations that govern the laws of nature and all this stuff, that does not change regardless if you shrink, expand, rotate your frame of reference, everything, all the dynamics should stay the same. So we want to keep that in mind as we go through with conformal field theory. So we're going to be looking at this also from a physics perspective, because if you look at this from just a straight math perspective, things get really abstract really quick. My apologies again for the dog in the background. Any contribution that you make is going to go to making an office space where you hear less noise and all that sort of stuff, but I diverge a little bit. So in this way, conformal field theory is going to be more concrete in our minds. From there, we're going to be able to understand conformal field theory more abstractly. And then we're going to start by considering transformations in which all the laws of physics, again, stay the same. So let's go ahead and get started just by looking at this image. So this image, we have a coordinate reference frame, and we are labeling x1 and x2. Usually this is the y dimension, this horizontal dimension. Or the horizontal dimension is x, the vertical dimension is y. Here we're calling x1 and x2 because we could have multiple orthogonal dimensions to our system. For right now, we're just looking at 2 dimensions. And the idea here is that from from the original coordinates, these should be primed. Oh, that is way too thick. It's the thickness of the pen. These are primed coordinates, so that's these coordinates. And those coordinates are a shift in the new coordinates. So this is going to be the old coordinates, right? So the old coordinates, and there's that shift in the new coordinates. And it's a small infinitesimal shift. And the key idea here is going to be that it's linear and it's very small, okay? The linearity is going to be important when we start deriving more advanced looking equations, and we're going to get to that in this video. A general form of the Pythagorean theorem reads this, right? So we can measure any distance in any coordinate frame using this equation, all we need is a metric, and that metric is going to when we talk about tensors, right? So this is really when we're talking about tensors, the idea here is that this here is the metric tensor, and then this is the basis for the metric tensor. And so every entry of the metric tensor, G11 for example, is going to have dx1. This should be, to be technical, it's a tensor product of basis. For right now, we're not going to get super technical about that. Really, how we can think about this from a very, very surface level understanding, which is really all we need for right now, is we can think of this as, I'll do this in green, whenever you're computing the distance in some coordinate frame, you have dx squared plus dy squared. That's the Pythagorean theorem, right? And we can write this as dx I plus dxj, or we can write this as dxi dxj Kronecker delta ij. And in a general sense, this Kronecker delta becomes this guy right here in flat space. In curved space, it doesn't. Right? So that's the relationship. That's the very quick and dirty way of understanding this. These are really just numbers that tell